My name is Igor Gengrossi, and I'm part of the pre-sales team for IP products at Nokia. I apologize for not being able to be present in the stage today to talk to you about this topic, but unfortunately I had some family issues that prevented me from traveling. This is a session that I'm going to talk about transport technologies for 5G, and it's pretty much a follow-up to the session that I did on NANOG 75, which was called 5G, an IP engineer perspective. So if you don't know anything about 5G transport, or if you haven't looked at any perspectives, please take a look at that video. That will help in understanding the technologies that I'm going to talk about today. So let's get started. I'll do this a very quick review in case you haven't seen anything, but in this slide you see a 5G core, which is represented by only a single icon in the top. And then you have the 5G radio. So one of the big characteristics of 5G is that there are three layers inside the radio, or three different components. There's a component called the RU, which is the radio unit, another component called the DU, which is the distributed unit, and another component called the CU, which is the centralized unit. This architecture was built essentially with the goal to have some of these elements running in a virtualized environment. So the CU pretty much is the easiest one to be in a virtualized environment. It runs all the non-real-time processes. The DU, many times still today, runs on proprietary hardware. It is becoming more common also to have that going to a virtualized form factor. And together with the RU, they run the real-time processes. So that's why you see those two intra-radio interfaces there with the name real-time and non-real-time. Sometimes it's called non-real-time interface and real-time interface, so F1 interface for the connection between the DU and the CU, and then the connection between the DU and the RU. So the name in which those network segments are more known is front haul, for that connection between the RU and the DU. Mid haul, which is the connection between the DU and the CU, and then the connection that already exists today, which is called backhaul. So that is from the radio all the way to the 5G core. So that is external to the radio. That still exists today. And a little bit of those differences in the intra-radio interfaces are related to primarily latency and bandwidth. So the closer you get to the RU, more bandwidth you need and less latency you need. Okay, so when we start looking into building a network for 5G, what happens is that very few operators are going to build a new network. So most of them are upgrading what they already had in place for 4G. And because of that, there's not only obviously bandwidth upgrades, which is expected because of the higher bandwidths of 5G, but there's also some key technologies that are needed to make all of this work. And in the next few sections, I'm going to go through some of these key technologies. So the first one that I'd like to start with is front haul. Front haul, it is a technology that already existed in 4G. Depending on where you were in the world, it would be more or less deployed. But front haul was primarily created in 4G with the idea that you might have a big, large building, and you put all of the baseband processing on the bottom of the building, and you put the antennas on the top of that building. So you needed some sort of protocol to take the antenna samples all the way from the radio to the baseband unit processing. Because if you just put a waveguide, that would have a lot of loss. So the digital way of doing that was a protocol called CPRI. And that's what you see in the left side of the slide. So CPRI is an agreement of an implementation for digital antenna samples. So that's primarily this. You get the samples from the antenna, you send those samples throughout this digital protocol. It is a TDM-based protocol, primarily used with optical connections. Could be used with electrical as well, but mostly used with optical. And it's a constant bit rate, just because you're getting every single antenna samples, every single radio sample, and sending that through a digital interface. It is a constant bit rate, so it doesn't matter if you have many users connected to the radio, or if you have no users at all connected to the radio, you're always going to have that same bandwidth. There are a few other interesting perspectives here on CPRI. One is that it carries synchronization. We're going to have a whole section on synchronization, and I'll go into more details, but the CPRI used for 4G carries embedded synchronization, so that's very important. And there's also some control and management protocols that come with it. So because the CPRI protocol does not vary with either usage, or it only varies, better said, with the number of antenna items or antenna elements that you have there, and with the spectrum, the frequencies, the frequency band that the radio is operating. When we look at evolving that radio to 5G, that protocol would become cost prohibitive, just because we have more band in the radio itself, the frequencies, and also a lot more antennas with MIMO. So in order to enable that connection between remote radios and centralized processing in 5G, another protocol had to be built. And the protocol that was built was eCPRI. So you see on the right side of the slide, the eCPRI protocol stack. So the basic idea here is just to get CPRI over packet. And in this case, this packet is Ethernet. So you can see the Ether type and the bottom. You can see many familiar protocols here in the screen as well. So it is a Ethernet-based protocol, but you have also an optional IP layer that makes it easier for you to transport that through different types of infrastructures. One of the important things to note is that eCPRI doesn't carry synchronization just like CPRI did. So because of that, now with eCPRI, we need the network to provide synchronization for the application, which is the radio. And that's what we're going to talk about in the next section. And the biggest benefit of using eCPRI now is that it allows the potential sharing of that Ethernet circuit between the radio and the centralized processing. In this case, it would be the DU for 5G. So there's an additional TCO benefit on top of that fiber that you can achieve with eCPRI. Now, when you start looking at how to transfer those packets for front haul into an Ethernet segment, can we use a simple Ethernet switch? Well, yes, we can, but there are some careabouts that we have, or some concerns when transporting eCPRI, because it's a very time-sensitive protocol. So the IEEE created a standard called the 802.1cm, which is actually a set of already established standards. You see some of those standards in the left side of the slide in the table, and that table is not comprehensive, but shows the most important ones. And also some traffic requirements, which you see in the right side of the slide. So essentially, we're talking about just 802.1q bridges with VLAN, spanning tree if you want. I don't think anybody is deploying layer 2 broadcast domains anymore, but you could potentially use that if you need it. At least 3 priority queues, with 1 being strict priority. So strict priority is mandatory because all of the CPRI frames need to be on a strict priority queuing. Then synchronization, we see 8275.1 telecom profile. Again, we're going to talk about that in the next section of the presentation. And also synchronous Ethernet. So again, because eCPRI does not carry synchronization, that underlying infrastructure needs to provide synchronization. And then you have in the bottom of the table two standards that you might not be familiar with. So one is interspersing express traffic, and also frame preemption. So what is that? So that is the ability for you in an Ethernet segment. If you're transmitting a lower priority frame and a higher priority frame arrives in the queue, you stop transmitting that lower priority frame, transmit the higher priority frame, and then resume the lower priority frame. So the basic idea of frame preemption is just to reduce jitter. There's two profiles with 802.1cm. One called profile A, where you don't use that, and another called profile B, where you use that. And the rule here is that if you're mixing non-front haul and front haul traffic, and the non-front haul traffic has packet sizes larger than 2,000 bytes, then you need frame preemption to maintain the jitter into acceptable values. And then you see on the right the different requirements in terms of delay and packet loss for the typical eCPRI traffic that you see in terms of user plane, control and management plane, both fast and slow. So now we have a set of guidelines essentially with 802.1cm of how to transport those signals from the radio all the way to a centralized processing unit over an Ethernet segment. But the reality is that a lot of those sites, if not all of the sites today that have some sort of centralized processing, they are using CPRI. And no operator will simply upgrade the entire infrastructure because it's cost prohibitive. It would take a lot of money just to replace all of the deployed radios over there. So the reality in all of the deployments where you have some centralized processing is that you're going to have to deal with CPRI and eCPRI at the same time, most of the times, unless you're a completely greenfield deployment. Most of the times when you use CPRI, we're using some sort of WDM multiplexing, so just essentially light multiplexing. And we can use that with CPRI as well. So that is an option, and there's operators just taking advantage of new wavelengths just to use eCPRI. That is completely valid. But what if we thought about a way to use a native Ethernet link between those two sites, even with the CPRI? So that's what the IEEE worked on. And with that, a new standard was created, the 1914 Radio over Ethernet standard. So that establishes how we can transport CPRI or encapsulate CPRI over Ethernet. And in this case, Ethernet, we call Ethernet TSN because we need all of those prioritization and traffic requirements met in this case. So the basic concept here is to have an ROE mapper and a demapper, which will convert CPRI to Ethernet and Ethernet to CPRI on the other side. You have the Ethernet encapsulation in the bottom of the slide, so you can see the Ether type. It's pretty simple, just a plain Ethernet frame as we know it. And another important information is that the mapper and the demapper needs to be synchronized. Again, CPRI carries the synchronization frames between the radio, the RH, and the BBU, the baseband processing unit. So we need that time and phase synchronization there. So again, we're going to talk about plenty of synchronization concepts in the next slide. But now, when we look at this nodes transporting CPRI over Ethernet, CPRI has a characteristic that, although it is a standard agreement, the actual implementations are proprietary in terms of each radio vendor. So you cannot mix the BBU and the RRH between two different vendors. That's the reality of 4G. In 5G, the ORAN working group 4 is working on specifying that, and other working groups as well is working on specifying an open eCPRI implementation where you can mix and match all of those different vendors, but that is not the reality in 4G. So there is some sort of proprietary aspects when looking at CPRI. So because of that, there are 3 different ways of doing radio over Ethernet. So the first way is called structure agnostic tunneling mode, sorry. So that means that we just look at the layer 1 signal coming into the mapper. We create a constant bit rate bit stream, and we just do a demapping function in the other end. So essentially what comes in comes out at a layer 1 level. So we're not looking at any higher layer protocols. This provides us the best level of interoperability, and can be used with any protocol essentially. It is a constant bit rate bit stream, so it provides the highest bandwidth consumption possible. So that might not be desirable, but in some circumstances that might be the only option available. Then we can go to the next mapper in the middle of the slide, which is the structure agnostic, but line coding aware. So the line coding aware mode, what we do is we remove some of the line coding bits. So CPRI comes both in 8B, 10B, or 64B, 66B. In this case, we would be left with only the 8B or 64 bits in this case, so we would remove some bits. This provides us some savings in terms of bandwidth, not a lot. And 8B, 10B a bit more than 64B, 66B. But because we are looking at frames here, we require a little bit of understanding of higher layers. And again, highly interoperable, but with a little bit of bandwidth savings in this case. And the third mode is structure aware. So in this case, we need the full understanding of the CPRI protocol. So what we're gonna have to do is open up the CPRI protocol entirely, remove all of the unused bits, decompose the data flows, control flows, and the timing synchronization flows of CPRI. And obviously, because we're doing all that decomposition and optimization, it saves us a whole lot more bandwidth. But again, we can only do it if we fully understand the CPRI implementation. So this is a vendor-specific that is tied to the radio implementation. So you need to mix, need to match that CPRI ROE implementation with the radio-specific radio that we're working with. So those are the three types of ROE mappers, and with that, we can use now a fully packet-based infrastructure to transport both the new eCPRI packets that come in the newer radios, as well as the CPRI radios, and create a fully packet-based infrastructure for front haul. So centralized radio still, as of beginning of 2022, has not been so widely deployed. Many of the 5G deployments have been relying on distributed radio, which means that that is not decomposed. So CU, DU, and RU are deployed together. There are a few deployments out there already centralized and decomposing those elements, but moving forward, there's a lot of expectation that front haul is going to be a very important technology. So ROE and eCPRI become fundamental for that. Okay, so now let's look at another fundamental capability for 5G transport networks, which is synchronization. So why do we need synchronization first in mobile networks? So the basic principle of a mobile network is that you need movement, right? So you need to move from one place to the other without losing connection. Because you're using the same medium, a shared medium, which is the air interface, a frequency in the air interface between the different radios, we need those radios to be synchronized in order for the network to provide the ability for any given device to move between one radio and the other and finish transmission with a specific radio and resume transmission and reception with another radio without losing traffic. So that is why we need synchronization. That is why it's a fundamental capability. We sometimes even say that synchronization in mobile networks is just like power. If you lose synchronization, everybody is isolated. Essentially, you don't have any more movement. As radio features evolved, some capabilities such as carrier aggregation, which is the ability to share two radios, or actually use two radios sharing to a same device, that capability puts even more strict requirements into the synchronization of those radios. So they need to be even more tightly synchronized in order for the network to take advantage of those capabilities. So at the end, it is the radio capability or the radio capabilities that are going to drive the timing, the synchronization requirements. It's also important to note that there are two types of synchronization. And they highly depend on the type of modulation that the radios use. So if the radios use FDD, which was used a lot more in 4G, that was the predominant type of modulation for 4G. FDD's frequency division duplex. So essentially you're saying that you have a specific frequency band for transmitting and another frequency band for reception. Then you need frequency synchronization. And some of the technologies that provide that is GNSS or GPS. There are other types of constellation that also provide the same capability. SONET synchronizes in frequency, synchronous Ethernet, same thing, and PTP 1588 also can synchronize frequency. There's another technology for modulation, which is time division duplex, which is TDD. In that case, we don't have separate frequency bands for transmitting and receiving anymore. We have a single frequency band that is logically split into reception and transmission. So for that case, we need time and phase synchronization as well as frequency, just because we need to split that same frequency band into transmission and reception. And there are typically two technologies used for that, GPS or GNSS or other constellations as well, and 1588 PTP. Those are the two technologies used in this case. TDD becomes a lot more prevalent in 5G because a lot of the frequency bands determined for 5G use TDD. So in that case, we're going to see a lot of discussion around time and phase synchronization to enable 5G. So let's take a look at the basic network timing distribution concepts. And before I talk about this, I think I need to make a disclaimer here, which is the IEEE is still working on specifying an inclusive nomenclature for IEEE 1588. So there's a PAR going on called the P1588G. If you're familiar with 1588, it uses a lot of terms, master and slave. The final terms that are going to be chosen are not yet defined. There is a proposal that might go through, which is time transmitter and time receiver. So for the purpose of this presentation, I'll try to stick with transmitter and receiver. Whenever I talk to transmitter, if you don't know what that means, that is replacing the word master, and receiver would replace the word slave. Here you have essentially a protocol which is defined by the IEEE 1588 Precision Time Protocol. And it uses this transmitter and receiver concept where one node sends timing to another, and then this the next node is going to send to another one, and so on and so forth. So there's a general protocol specification, but there's also some profiles that establish how that protocol should be used in the specific applications. And we have some telecom profiles, which, as the name implies, establish how those profiles need to be used on a telecom environment. The two main telecom profiles are G8275.1, and by the way, those profiles are defined by the ITU, not by the IEEE. So the ITU G8275.1 is for full timing support, so that sometimes you're going to see FTS as the acronym. That means that all nodes across the path must support timing capabilities or must support PTP. It uses Ethernet encapsulation, so it's a node-to-node Ethernet encapsulation, and provides phase and time only synchronization. So for frequency, G8275.1 typically uses synchronous Ethernet, which is a physical technology. So it's provided by the underlying physical signals of the Ethernet links between two elements. And then the other profile is G8275.2, which is for partial timing support. So that means that only a few nodes in the network are going to support timing. And you need to traverse a non-PTP aware network. That is why, in this case, we're using UDP over IP encapsulation, because we need to traverse non-PTP aware networks. And for G8275.2, it does provide frequency, time, and phase synchronization. So we also have some common nomenclature here. So PRTC is a primary reference time clock. So it is typically a GNSS receiver. Could be other types of references, but for this presentation, let's think about a GNSS receiver, which is the most used PRTC type. Then we have the Grandmaster, and the Grandmaster in this case is the one that provides timing receives the time reference and provides the PTP packets. Looks like the Grandmaster term is not going to be a topic of this nomenclature revision, so we'll see how that looks like. For now, I'll just, they're typically deployed together, the Grandmaster and PRTC, so I'll just refer to them as time references. So whenever I say the time reference, I'm talking about Grandmaster plus PRTC. So those are the time references. And then you have this concept of boundary clock, where you get the PTP messages on the reception side, you synchronize your internal clock, and then you transmit the PTP messages to the next node in the path. So that is the boundary clock. That is essential for us to provide the better accuracy, because it corrects for some error. We're going to talk about error in the next slide. At the end, we have the receiving clock, the TTSC. So it's the time receiver, where you essentially get the timing signal and use that time to synchronize your internal systems. There's also a transparent clock, which I'm not covering here, but that is also a valid node. It's not so widely deployed as boundary clocks, so we'll just stick with boundary clocks because it provides better accuracy. Now, whenever you transmit timing through the network, we are introducing error. And ITU has defined some limits to the time error that each type of node can introduce in the network. So you see for the boundary clocks and the receivers in the left, and you see for the time references on the right. Typically you have on the boundary clock and receivers, the classes A, B, and C, with class C being the most accurate. And here you can see there's some specifications in terms of both constant time error as well as dynamic time error. I didn't put all of the requirements in this table just for conciseness, but please look at the standard, the G8273.2, so you can have all of the requirements for those nodes. And the same goes for the time references on the right. You can see there's different types of references: PRTCA, PRTCB, and ePRTC with different accuracies. What is important to note is that it's not only the nodes themselves that add error, that add time error, but there's also other sources, such as, for instance, link asymmetry. So if you have, for instance, in a link, different lengths of fiber in the transmit and receive fibers, that is going to add some time error because of link asymmetry. And that is sometimes more common than it might look like. Another source of time error is temperature variation. So the temperature, because we're dealing with things like crystals and oscillators and components, electrical components, as the temperature varies, they might affect the accuracy. and the time error added by each element in the network. And the components themselves are also some source of variation. So even using very strict tolerances for the components, sometimes when you're running tests, you run a test, you switch off or power cycle the node and switch it on again and run the same test. And you're going to see a slight difference there. And this is an area, timing is an area where, because of all of those variations, you typically want to have a very tight hardware and software development, because the same code for different hardware implementations needs to be tuned specifically for having better accuracy on that specific hardware implementation. Or sometimes you need to tune a little bit the hardware for that code to work well. So it goes both ways. And it's a very sensitive area in terms of feature development for any vendor in the industry. So those are the time error. And again, when we're transmitting synchronization timing throughout the network, we're going to add error. So how much error is acceptable for 5G? So here we have a diagram that shows the different requirements. We'll start with the right side of the slide, which shows the basic requirement for 3,000 nanoseconds. So that is the basic requirement from 3GPP, where you need to have 3,000 nanoseconds between any two radios in order to enable the handoff between the two radios. So that is the maximum admissible time error difference between any two radios in a mobile network. With that, we create essentially three categories of timing accuracy requirements. So I'll start from the bottom of the table on the left, and that's category C. And we here have the value of 1,500 nanoseconds, 1,500 nanoseconds. Sometimes you see 1.5 microseconds as well. Obviously the same thing. So 1,500 nanoseconds comes from the fact that if you have 3,000 between any two radios, between the antenna, the radio one, and the time reference, you're going to need 1,500. So you can have 1,500 from reference to radio 1 and 1,500 from reference to radio 2. That's where the 1,500 nanoseconds number comes from. So that is category C. You see some of the radio features. So the basic 5G TDD requirement just needs this absolute number, absolute meaning from the radio antenna all the way to the time reference. Now, when we start looking at more advanced functionalities in the radio, we have two other categories. And those, again, are needed when we are looking at any two given radios talking to a single device at the same time. So we are actually sharing those two radios to send and receive signals to one device. So that is for carrier aggregation, typically could be intraband or interband. And then we have category B, which is 216 nanoseconds. Category B is typically used in intra-site, but could also be used inter-site because it's a little bit less stringent than category A, which is 130 nanoseconds. So that is typically only used intra-site. So in the same cell site, in the same location, two radios that are physically located together. Now, because we're talking about those two radios, in this case, that these numbers, 260 and 130, are not absolute, meaning that they are not between the radio and the time reference, but rather they are between two antennas of two different radios that are serving a single device, right? So that is a very important distinction to have here. Category C has an absolute time error requirement from the antenna all the way to the time reference. Categories A and B have a relative time error reference or requirement between any two given radios. So that is how we look at the maximum time error. Now, how can we budget for that time error? So This next slide is directly taken from ITU G8275.71, which shows the performance for, in this case, full timing support, FTS. And this is the case for backhaul only. We're going to talk about front haul in a second. So in this slide, you can see a PRTC, a time reference that will give you 100 nanoseconds. Then you have some dynamic time error. Then you have some constant time error, and you have something left for the time error of links. In blue, you can have boundary clocks class A, and in green, you can have the boundary clocks class B. So you can see that class B boundary clocks give you more hops than the class A boundary clocks. And that's the effect of those different classes of boundary clocks. The more accurate your boundary clock is, the more hops you're able to traverse without going over the budget. And in this case, you can see that there's 1100 nanoseconds all the way from the reference to the radio, because the radio is considering some budget for short-term holdover, which means if the radio loses synchronization with its reference, it can just select another reference, and that will include a time error. So that is the 250 nanoseconds in red you see here on the right side. And then you have 150 nanoseconds for the radio itself. So that's how you come from 1500 end-to-end from the antenna to the time reference to 1100 that you see many times in collaterals in the network. So that's how it's calculated. There's actually some formulas in the standard that allow you to calculate that very well. I'm not going to go through that. It's outside of the scope of this presentation. But there is a mathematical way of calculating those budgets. Now, the bottom part of the slide has a different scenario. In this case, we don't have that 250 nanoseconds in the radio anymore allocated for holdovers or for reselection. We transfer that reselection budget now to the boundary clock. So it means that a given boundary clock will lose its reference and will select another reference as a backup. And then you have that very large budget for that of 620 nanoseconds. You still have the dynamic time error, still have the constant time error. You can see the class C boundary clocks introduce a much less time error, so you can potentially have a lot more hops of boundary clocks in this case, and then you also have the time error for the links. So in this case, because we don't have that 250 nanoseconds for the radio, the network budget ends up being 1350 nanoseconds. So that's why it's important to understand how these budgets are calculated, because the real number here is 1500 between the time reference and the antenna. Whatever is in the middle highly depends of the types of nodes that you're using and their specific characteristics. So you need to understand that and calculate the limits for a specific network application. So how does the deployment look like in this case for backhaul? So the most typical deployment is to have what we call a cell side router, which is a router that goes in the cell side connected to the GPS. So it becomes a time reference for those radios. And those radios are typically directly connected to the cell side router. I'll just mention that the cell side router is an industry term that is highly used. But then when you're starting to use centralized radios where you might have the CU all the way into the network in a more centralized location, that first hop router is not going to be inside the cell side anymore. So it's going to be in maybe an aggregation side. So in centralized RAN locations, the cell side router term might not make a lot of sense. But anyway, I'll stick to cell side router here. Every time I say cell side router, it is the first hop router. So in this case, because they're directly connected, the time error introduced here is essentially that of the time reference, the PRTC, and also of the links. And then obviously you always have the time error introduced by the radio. So it is very likely that you're still okay in using inter-site category B if you need it, because all of the sites are going to be referenced with a GPS. Now, if you want some backup, what if that GPS fails? And yes, the GPS does fail. So it could be maybe jammed. There's ways to try to prevent that a little bit, but it could be jammed. Or if you don't have a good antenna positioning for the GPS, and that typically happens in urban canyons, think New York City, for instance, or anytime you were driving in a very high building type of street in downtown, you probably lost GPS in your car, and that happens the same thing with the GPS for the router. So if you don't have good visibility for the satellites, you might lose GPS from time to time. So if you lose that, you need a backup. And in this case, if you own the fiber infrastructure and you were able to provide full timing support all the way to a backup centralized time reference, you could essentially just switch to that more centralized location in case the GPS fails. Depending on the path you have from that south side to your centralized location, you might or might not be okay for inter-site category B. So it depends on the radio features. Again, you need to dimension this path according to the radio requirements in terms of time error. But this is typically how you do in the case you own that fiber infrastructure and you're able to do full timing support to a backup time reference. Now, what happens in case you don't own that fiber infrastructure and you still want to provide some sort of redundancy for your GPS? So in this case, because you don't have a PTP-aware network, and many times those are Ethernet circuits, with all types of companies, and I'm sure there are some people in the audience here that even are part of these companies that provide connectivity to those mobile operators. You will need, and you in this case, the mobile operator will need to operate into PTS mode, partial timing support mode, right? So in this case, there's going to be an Ethernet circuit connecting an aggregation site to a cell site, and you have a GPS in the cell site, but then you have this PTS, this partial timing support connection all the way back to your time reference. So what we do in this case is we actually use a slightly different standard, which is called APTS, and the A comes from assisted. So assisted PTS means that the GPS that is in the cell site will adjust the time error that is in the that comes from the PTS network. So in that case, the PTS network will introduce a lot more time error because those nodes are not PTP aware. So the GPS will provide a very stable reference. The router will correct that time error. And in case the GPS goes away, it can send a more accurate signal to the RAN. Now, if the network in the back, the Ethernet circuit has a traffic spike or has buffering problems or has reroutes or the number of hop changes because of reroutes, that reference that the router established with the GPS is not valid anymore, and that is going to be have an effect into the signal, the timing signal that goes to the RAN. So important to say that APTS is a G8275.2 standard. If you don't want to use G8275.2 in the radio, you need some interworking function in that router to convert G8275.2 to G8275.1. Quickly talking about front haul synchronization. So there's 4 different topologies that all RAN specified. Configuration 1 has the time reference in the DU connected directly to the RU. The configuration 2 has some boundary clocks in the middle between the DU and the RU. Configuration 3 has the timing reference between the DU and the RU. And configuration 4 has independent time references between the DU and the RU. So if we look in more details how that looks like in terms of budget, you see that this is no different. You still have the 1500 nanoseconds all the way from the antenna to the time reference. So what we need to be aware here is that if we are doing some inter-radio features like carrier aggregation, or in other words, category B or C, because those references are going to be between any given two radios, we always need to look at the last common boundary clock. So if we look at the two RUs in the top, the last common boundary clock is the one inside the site. So that is going to be fine because they're locally connected. But if we look at radios from the site in the bottom to the site in the top, like between those two sites, the last common boundary clock is going to be the one in the hub site. And then we now need to see if that budget is okay for intersite, for that intersite capability. So here you have some formulas and to show you the way you think about that. And last, for front haul, in the C3 deployment, the main point of this slide is to show that the real requirement for front haul is to synchronize the RUs and not necessarily the DU. The DU has a more loose synchronization requirement. We typically say it also needs 1500 nanoseconds. So this means that you need to be concerned with the synchronization between any given two RUs and from the RU to the time reference. So that means if you have to choose a location to put your time reference, that probably should be closer to the RUs than to the DUs. The DU is a lot looser, is not so strict in its synchronization requirements. So into the last section of the presentation, 5G network slicing. It's probably one of the most talked about capabilities. And let's take a look at 5G network slicing and what it means for everyone. So first, let's define what is network slicing in 5G. And I try to put it into some well-known words. And my definition is that it is a network-controlled, SLA-backed, clientless VPN. So let me go through that. It's network controlled because the operator controls that VPN. So the operator needs to provision the slices in all elements of the network, including the devices themselves. And it will operate and needs to create those slices before you can even use it. So it is network control. It will control who uses what and where. It is SLA backed because every node in the network, and you can take a look at the different roles they have here in the slide, every node is able to apply QoS, quality of service, and prioritize traffic from each slice accordingly, or according to any SLA that it needs to use in terms of bandwidth, latency, queuing, anything that you might think about. This is the biggest actually difference of network slicing when compared to some similar technologies such as APN that we had in 4G. It is clientless because it's a native capability. So every 5G device already uses slicing. So it is enabled by default. Even if you're not selecting any slice, you're selecting this default slice, which will typically be internet traffic. It's not something that you enable later. So every 5G connection has a slice associated to it. So there's nothing needed to install there. And VPN, because it gives us the same feeling of being connected to a VPN. It is a virtual instance, a logical instance on top of the network, including separate routing context. That means that you have completely separate IP addressing and completely separate traffic isolation. And here you can see all of the nodes in the network and some of their roles in network slicing. So if you're using network slicing, let's take a look at a specific use case, and this would be an enterprise application, enterprise app application. Maybe it's some sort of control app, or maybe couldn't be even protected email or whatever application you want to think about. So in this case, instead of installing a VPN client, for instance, to use that, the enterprise could go and talk to an operator and say, hey, for this specific application, in my employees' devices, I need you to protect that traffic and route that directly to my internal network and not have any connection to the internet or any other network. So the first requirement here is obviously that agreement between the enterprise and the operator to establish, so that the operator can establish the slicing infrastructure and provision all of that into the network. Then the enterprise, and here in this slide, I'll just mention that I'm showing the Android specific implementation. You have a link in the bottom of the slide that has a little bit more details on how Android implements this. So you need to enable slicing through MDM, through device management. So the enterprise will tell the device, hey, you need to use slicing. And then the network operator will send a message to each device. This message has a slicing selection configuration in a message called URSP, so UE Route Selection Policy. This message comes from a node inside the operator called the PCF. It's the policy control function. It flows to the control plane element, which is called AMF, access and mobility function. Those are all 5G control plane elements. So the operator needs to configure all of those devices to send this message. And you have an example in the left, what that message looks like. Obviously a simplified example. But once the device receives that message, what it's going to do is it's going to say, oh, okay, for the app X, I need to use slice enterprise, and the slice ID is this one, SST1SD2. So that is just how slices are configured, the ID inside the 5G core. So in this case, it knows that it needs to connect to the specific enterprise slice. It will receive a specific IP address. It will create a specific routing instance and connect that app only to that routing instance, which is a private network. In essence, this is just like an EVPN, but you don't need to install or deploy an EVPN client here because it's native to 5G, with the added ability of the 5G operator being able to provide an SLA for this specific VPN. Now, if you're a network builder, if you're a mobile operator, what does it mean to you? Well, it's just another type of network virtualization. We have been doing virtualization in IP networks and Ethernet networks forever. So what is each slice? It's just another VPN. It's a layer 3 VPN. So the radio is going to use different IP addresses, one for each slice. And it's important to note that if you take a packet from the network, if you capture a packet, you cannot tell which slice it belongs to. It doesn't have any slice identifier. So you need a service delimiter in the radio to tell the first hop router, the south-side router, or the PE, the first PE, which slice those packets belong to. And in this case, VLANs are the service delimiters here. So essentially, the radio is going to deliver each slice in a dedicated VLAN. So if you provision another slice, you're going to get another VLAN. And those VLANs are going to be mapped through VRFs, in this case, in the first hop router. You can see here there's a blue and red VLAN and their GTP tunnel. It's important to note that the traffic from the devices are always tunneled. And this poses an interesting point, which is the radio could also potentially use a single IP address for all slices and still have traffic separation, because the GTP tunnel separates the device traffic from the infrastructure traffic. The only caveat is that if we only use a single IP address in the radio, we cannot have traffic separation. All slices are going to be treated just like one, but we still have, and I mean traffic separation in the infrastructure and different queue costs, but there's still going to be traffic separation between all the different VPNs. You're never going to mix and match, regardless if you use different IPs in the radio or only a single IP. So obviously, if you want to provide different calls and different priorities and so on and so forth, you want to separate that into different VLANs. And again, you go into different VRFs. Now, In the core, the most used technology here is MPLS. You could also use segment routing MPLS. There's lots of discussion and some operators looking at SRv6. So you could use traffic engineering embedded into the network. You could use centralized controller for traffic engineering. Here is just pick your favorite tool that you like to use and apply the policies that you need to make it happen. And what about control plane? Same concept. Control plane is just another VRF, and it's going to be separated. You also have management plane, which I didn't put here, which is, yet another VRF. The only different case which I wanted to show in this slide is synchronization. So synchronization, as we saw before, in case we're using G8275.1 full timing support, we use Ethernet encapsulation. So the synchronization packets are going to come untagged. So you need to make sure that you can pass untagged packets here if there's any devices in between the radio and this first hop router, because that's how the synchronization is going to be transmitted. So another important point here is that the network typically connects, the 5G radio network typically connects to a 5G core that is typically deployed in a data center, be that a private data center or a public data center. So when we look at a data center, probably the most typical protocol used there is VXLAN. So in this case, we're going to have some sort of data center interconnection here, node, border leaf, whatever you want to call it, that has the VRFs and map those VRFs to VXLANs inside the data center fabric. It could vary, doesn't need to be VXLANs. In fact, if you go maybe to a public cloud, could be something different. But most of the cores, if not all of the 5G cores, are starting to be deployed in the form of cloud native applications in Kubernetes. So here is just typical data center design where you have IP traffic coming into a Kubernetes cluster. Pick your own tools as you prefer. Doesn't need to be VXLAN. It's just an option that I'm showing here as an idea of how we would do that in the data center border. And just a quick slide on the end-to-end architecture. So we have all of the encapsulations here from all the way in the left from the radio to the core. You have eVPNs, you have IP VPNs for layer 3 VPNs, BGP, RMP, BGP being the control protocol end-to-end, makes it easier to provision end-to-end, could be segment routing or maybe segment routing v6 as well here. Many options, again, pick and choose your favorite technologies. 5G doesn't dictate what you need to use. It's just, an IP network would cost and layer 3 VPNs essentially. So we've been building those networks forever, so it's just another case. And last topic, last but not least, QoS, very important. I've been talking about, hey, you can provide an SLA. So how does that SLA work? In this case, 5G is a little bit better than 4G because 4G only allowed us to prioritize the GTP tunnel. So every flow inside that tunnel, regardless if it's Netflix or Facebook or WhatsApp or whatever application you're using, they all get the same priority. In 5G, we can differentiate all of that, and the radio will mark the DSCP for all of these different flows. So in this case, we can take the router and apply different classification based on criteria based on the SCP and apply different QoS policies. So it makes our lives easier when doing prioritization. So if we look at the end, how that looks like from a router perspective, you're going to have all the slices, all the VLANs, where we apply hierarchical QoS. So hierarchical queuing with all of the high, medium, low, in this case, priority traffic coming into the different VLANs. They're going to be coming marked with the DSCP. Then what we're going to do is we're going to mark those packets, in this case for MPLS, we're going to mark the MPLS TC field and have flat queuing in the core. So essentially IP QoS 101, again, no different than any layer 3 VPN type of infrastructure that we've been building forever. So slicing will just make use of those technologies that have been highly effective up to today. All right, so that concludes the presentation. It's a lot of material, I realize. I hope this median with the recording didn't take away from the content of the presentation. Thank you again for staying with me all the way through the end.
Igor, thank you very much. We really enjoyed this. Thank you.
Thank you for the opportunity.
Thank you. If there are any questions in the room, please do come in front of the mics. No questions in the room for you, and no questions for you as well on the chat. So if anybody wants to contact Igor, his contact details were on his presentation on the last page. Please do feel free to contact him. Igor, thank you very much again.
My pleasure. Thank you.